There is one thing you have never once doubted in your entire life. Not your memory, not your senses, but the space around you and the steady passage of time. And tonight I want to gently pull that certainty apart, because a growing number of serious physicists now suspect that space and time are not the foundation of reality at all. They have started saying it out loud. Space-time, they say, is doomed. Underneath it lies something stranger. Tonight we follow the trail, from Newton's fixed stage, through black holes, to the quiet idea that everything is woven from pure information. So, settle in, get comfortable, and let me show you what you have been standing inside all along. Most great questions in science begin with something strange, some oddity that nags and itches, until somebody is forced to explain it. This question is different. This one begins with something that has never once struck you as strange, something so utterly ordinary that asking about it out loud feels almost foolish. Pause for just a moment and notice the room you are in. Notice the distance from where you are sitting to the nearest wall, the few feet of empty air your hand could sweep through. Notice the quiet way this moment is already sliding into the next one, and that one into the one after. Space and time. You have moved through both of them every single second you have ever been alive, and the odds are you have never seriously asked what either of them actually is. That blind spot, that one corner of reality too obvious to ever question, is exactly where this story begins. And the reason it begins there is that the not asking is the whole problem. We treat space as the empty box the universe comes in, and time as the steady drumbeat playing somewhere in the background. And because they are always there, behind everything, we look straight past them. They are the stagehands of reality, so reliable that we forget they are on the stage at all. But the things we never question are exactly the things most likely to be hiding something, and in this case, what they may be hiding is the biggest secret in all of physics. Because a growing number of very serious physicists, the kind who win prizes and run laboratories and fill chalkboards with equations that actually work, now suspect something that sounds almost absurd when you first hear it. They suspect that space and time are not the foundation of reality at all. Some of them have started saying it out loud, in lectures and papers, with a phrase that would have gotten you laughed out of a physics department a generation ago. They say, space-time is doomed. They do not mean the universe is ending. They mean something stranger. They mean that space and time are not the bottom layer of what is real. They mean that underneath them, holding them up, there is something else entirely. Let me give you the idea that makes this thinkable, because once you have it, the whole thing stops sounding like science fiction and starts sounding like a question you should have asked years ago. Think about temperature. You know what temperature is. You can feel it right now. The warmth or the cool of the air on your skin, it is real. But here is the thing about temperature that most people never pause on. A single molecule does not have a temperature. One lone atom drifting through empty space is neither hot nor cold. Temperature is not a property of the individual pieces. It only appears when you have trillions upon trillions of molecules jiggling around together, and what we call heat is really just the average of all that frantic motion. Temperature is real, but it is not fundamental. It emerges. It is a large-scale appearance of something smaller and more basic doing its thing underneath. Now, hold that thought, because the claim at the center of everything we are going to talk about tonight is this. Space and time might be exactly like temperature. Real, yes. You can measure them, you live inside them, they govern everything you do, but not fundamental, not the flaw. Instead, a large-scale appearance of something more basic happening at a level so small and so strange that the words space and time stop meaning anything down there. This is the distinction I want you to carry with you through the whole journey, so let me make it as clean as I can. In physics, Something is fundamental if it is the floor, if it cannot be reduced to anything more basic, if it is simply part of the furniture of reality. And something is emergent if it is a pattern, an appearance, a large-scale behavior that arises out of those more fundamental pieces. A traffic jam is emergent. It is real, it ruins your evening, but it is not made of traffic jam particles. It is just a pattern that cars make. The question we are chasing tonight is which of these two things space and time really are. Are they the floor of reality? Or are they the traffic jam, the pattern, the appearance of something deeper that we have simply never been able to see? And if it is the second one, then the obvious question, the one that should be keeping you up at night, is the one that physicists are now staking their careers on. If space and time are not the foundation, then what is underneath them? What is the thing that space and time are made of? I am going to walk you through the answer, or at least the best answer we have right now, and I promise you it is stranger and more beautiful than you are expecting. We are going to start with the universe you think you live in, the one with the fixed walls and the steady clock, the picture that one brilliant man drew so perfectly that it ruled the world for 2 centuries. Then we are going to watch a young patent clerk take that picture and bend it until space and time melted into a single fabric. Then we are going to find the place where even that fabric tears, where the equations break and reality refuses to answer. And from that tear, we are going to follow a trail of clues, through the strange mathematics of black holes, into the most radical idea in modern physics, the possibility that everything you see is a kind of hologram, and finally into the quiet, almost unbelievable suggestion that the whole thing, all of it, is woven out of pure information. I want to be clear about the spirit of this, because it matters. This is not a frightening story. Nobody who sits with these ideas comes away scared. They come away with something closer to the opposite, a kind of slow, settling wonder, the feeling you get when you realize that the universe is running on rules far stranger and far more elegant than anything your intuition ever prepared you for. So this is not about doom, despite the phrase. It is about looking at the most ordinary things you know, the space in front of you and the time you are living through, and discovering that they are among the most profound mysteries in all of science. And there is a personal edge to this that I do not want you to miss. If space and time are emergent, then that includes your space and your time. The few feet of room around you right now, the evening you are spending, the very sense that one moment is flowing into the next, all of it would be the surface of something deeper. You are not watching this story from the outside. You are standing inside it. I will even tell you where we are headed at the very end, because it is the part that surprises people the most. This is not just philosophy, not just clever people arguing over chalkboards. In the last couple of years, physicists have begun designing actual experiments, tabletop experiments, small enough to fit in a single room, that could test whether space-time itself is quantum. We may be the first generation of humans to get a real, measured answer to a question our species has been asking since the first person looked up at the night sky and wondered what the dark between the stars was made of. But before we tear the stage down, we have to understand how solid that stage once seemed. We have to go back to the man who built the most perfect, most useful, and ultimately most wrong picture of space and time ever created. A picture so convincing that you, right now, almost certainly still believe it, is less than break time equals 1s, is greater than. The picture I am about to describe is one you already hold in your mind, whether anyone ever taught it to you or not. It is the default setting of the human brain, and it was written down formally and mathematically by Isaac Newton in the year 1687 in a book that more or less invented physics as we know it. Newton's universe had 2 great pillars, and the first was absolute space. Picture an enormous, invisible, perfectly rigid container, stretching out infinitely in every direction. It is always there. It does not move, it does not bend, it does not care what is inside it. If you removed every star, every planet, every atom in existence, Newton's space would still be sitting there, an empty stage waiting for actors who may never arrive. Space, in this picture, is the fixed arena. It is the graph paper of reality, the grid against which all motion is measured. The second pillar was absolute time. Imagine a single, perfect clock, ticking somewhere outside the universe, and its tick is the same everywhere, all at once. 1 second here is 1 second on the far side of the galaxy. Time flows steadily, uniformly, and universally, the same for a stone, a comet, and a king. It pours forward like a river that has no banks and no source, indifferent to everything floating in it. Newton's time is the master metronome of all existence, and it never misses a beat. Now here is why this picture is so powerful, and why you believe it. It matches your experience perfectly. Look around the room you are in. The walls stay where they are. The space between you and the door does not stretch or shrink. There is a clock somewhere nearby, and it ticks at a steady rate, and you assume, quite reasonably, that it is ticking at that same rate for everyone you know, everywhere on Earth, at this exact instant. This is not a theory you had to learn. It is the water you swim in. It feels less like an idea and more like a simple, obvious fact about the way things are. And for 200 years, it was not just intuitive, it was triumphant. Newton's laws, built on this fixed stage of absolute space and absolute time, did things no human knowledge had ever done before. They predicted the motions of the planets. They explained the tides, the rise and fall of entire oceans, as the pull of the moon. They told you where a comet would be decades in advance, and the comet showed up, on time, exactly where the mathematics said it would. They guided cannonballs and bridges, and, eventually, spacecraft. When a picture of the universe lets you predict the heavens with that kind of precision, you stop thinking of it as a model, you start thinking of it as the truth. I want you to feel just how completely this picture conquered the human mind, because its success is the reason it became invisible. A man named Edmund Halley used Newton's mathematics to look at a comet that had blazed across the sky and declared that it would return in about 76 years, long after his own death. He was right. The comet came back, on schedule, as if the heavens themselves were obeying the equations, and we still call it Halley's Comet today. Think about what that means. A few marks on paper, built on the assumption of absolute space and absolute time, could reach decades into the future and tell the cosmos where to be. When your picture of reality can do that, you stop treating it as one possible story among many. It hardens into common sense, into the simple, obvious truth, the kind of thing only a fool would question. And that is precisely the trap. Because the more a picture works, the harder it becomes to notice the quiet assumptions buried underneath it, the assumptions that may not be true at all. But there was one quiet voice of objection, raised even in Newton's own time, and it is worth pausing on, because it comes back to haunt this whole story at the very end. A philosopher and mathematician named Gottfried Leibniz refused to accept absolute space. He asked a simple, nagging question. Is space really a thing, an actual invisible container that exists on its own, or is space nothing more than the relationships between objects, the fact that this is near that one thing is to the left of another? In Leibniz's view, if you took away all the objects, you would not have an empty container left over. You would have nothing at all, because space was never a thing in the first place. It was just a way of describing how things relate. Hold on to that idea, the relational idea, because 2 centuries of physics is going to circle all the way back to it, For a long time, though, Leibniz lost the argument, and Newton's fixed stage reigned. The first real crack did not come from philosophy, it came from light. As physicists in the 1800s studied light more carefully, they ran into something that simply should not have been possible inside Newton's universe. Light had a speed, an enormous one, but a fixed one, and the closer they looked, the more that fixed speed refused to obey the rules that absolute space and absolute time demanded of it. Let me put that speed in terms you can feel. Light travels at about 300,000 kilometers every single second. That is fast enough to circle the entire Earth 7.5 times in the time it takes you to say the word once. It is fast enough that the sunlight warming your face left the surface of the sun about 8 minutes ago, which means you have never once seen the sun as it actually is, only as it was 8 minutes in the past. That is the speed we are dealing with. And here is the part that broke everything. No matter how you moved, no matter how fast you chased after a beam of light or ran away from it, you always measured that same speed. Always. 300,000 kilometers per second. Every time, for everyone. That should be impossible. Think about it on the highway. If you are driving at 100 kilometers an hour and a car passes you going 110, that car pulls away from you at only 10. Speeds are supposed to add and subtract depending on how you are moving. But light does not play that game. Chase it as fast as you like, and it still races away from you at the full 300,000. The experiments that revealed this, most famously one performed by two scientists named Michelson and Morley, went looking for the signature of Newton's absolute space, the so-called wind that the Earth should feel as it ploughed through that fixed invisible container. They found nothing. The container left no fingerprints at all. It was as if absolute space simply was not there. So physics arrived at a fork, and only one path could be true. Either these careful, repeated, beautifully precise experiments were all somehow wrong, or Newton's fixed stage, the absolute space and absolute time that everyone believed in, was the thing that was wrong. The experiments kept being right. They were always right, which left only one terrifying, exhilarating conclusion. The stage itself had to go. And the person who finally took that impossible constant speed of light seriously, who looked at it and decided not to explain it away, but to follow it wherever it led, was a 26-year-old clerk working in a patent office with no laboratory and no telescope, just a pencil and a refusal to look away. What he did next did not just patch up Newton's picture. It melted space and time together into something Newton never dreamed of, and it is the next step down toward the answer we are chasing. Is less than break time equals 1s is greater than. In the year 1905, Albert Einstein did something that almost nobody else was willing to do. He took the strange, stubborn behavior of light, not as a problem to be solved, but as a clue to be trusted. Everyone else looked at the constant speed of light and asked, "What is wrong with our experiments?" Einstein looked at it and asked, "What if nothing is wrong? What if light really does move at the same speed for everyone, and it is our ideas about space and time that have to bend to make room for that fact?" That single shift in attitude produced what we now call special relativity, and it pulled the floor out from under Newton's universe. Follow the logic with me, because it is simpler than people think, and the conclusions are genuinely startling. If the speed of light is the same for everyone no matter how they move, then something else has to give, because speed is just distance divided by time. And what gives, it turns out, is distance and time themselves. They are not fixed. They stretch and shrink depending on how you are moving. Einstein showed that a moving clock actually runs slow. Not appears to run slow, not seems to lag because of some trick of measurement. It genuinely ticks fewer seconds than a clock standing still. Time itself slows down for things in motion. This effect has a name. time dilation, and I want you to understand that it is not a thought experiment or a clever story. It is measured constantly in the real world. Particles called muons rain down on the Earth from the upper atmosphere, and they live for such a tiny fraction of a second that they should decay long before they reach the ground. But they are moving so fast that their internal clocks slow down, time stretches out for them, and so they survive the trip and we detect them at the surface, exactly as Einstein's mathematics predicts. The faster you move through space, the slower you move through time. Speed, in a sense, is a trade. You borrow from one to pay for the other. And it was not only time that bent. Einstein showed that moving objects actually contract, growing shorter along the direction they are traveling. Length itself, the most basic measure of space, is not absolute. It depends on motion. Two of Newton's great certainties, the steady universal clock and the rigid, unchanging ruler, both came apart in the same stroke. But the conclusion that I think is the strangest, and the most important for our story, is what happened to the word now. In Newton's universe there was a single universal present moment, the same instant ticking everywhere at once. Einstein showed that this cannot be true. Because of the way space and time trade off against each other, two observers moving differently can genuinely disagree about whether two distant events happened at the same time. One of them says, these two things happened together. The other says, no, this one happened first. And neither of them is wrong. There is no fact of the matter, no master clock to settle the dispute. The universe simply does not have a single, shared now sweeping through it. Your present moment and the present moment of a galaxy far away need not agree at all. Let that sit for a second, because we are going to return to it when we ask what time really is. A few years later, in 1908, a mathematician named Hermann Minkowski looked at what Einstein had done and saw something Einstein had not yet fully spelled out. If space and time stretch and shrink to keep the speed of light constant, then they are not really two separate things. They are two faces of one single object. Minkowski wove them together into a four-dimensional fabric, 3 dimensions of space and 1 of time, and he gave it a name, space-time. For the first time, the two words in our title became one thing. Space and time were no longer the empty stage and the steady clock. They were threads in a single woven cloth. Then Einstein went further, and this is where it becomes truly mind-bending. In 1915, he published General Relativity, and it explained the oldest mystery in physics, gravity, in a way nobody had ever imagined. Gravity, Einstein said, is not a force. There is no invisible rope pulling the Earth toward the Sunday. Instead, mass and energy bend the fabric of space-time around them, the way a heavy ball sitting on a stretched trampoline makes a dip in the surface. And other objects, rolling across that curved fabric, follow the curve. The Earth is not being pulled by the Sunday. The Earth is rolling in a straight line through space-time that the Sun has bent into a bowl. The physicist John Wheeler said it best. Matter tells space-time how to curve, and space-time tells matter how to move. This was not just a pretty idea. It made predictions that Newton's physics could not, and every one of them came true. It explained a tiny wobble in the orbit of Mercury that had baffled astronomers for decades. It predicted that starlight passing near the Sun would bend as it crossed the curved space-time, and in 1919, during a total eclipse, astronomers watched the stars near the Sun shift exactly as predicted. The fabric of space-time was real, and it could be bent, and here is the part that should make you trust this completely, because it is not in a textbook, it is in your pocket. The global positioning system, the thing that tells your phone where you are, depends on satellites carrying atomic clocks. Those satellites move fast, and they sit higher up in the Earth's gravity, where space-time is curved a little less. Both effects change how their clocks tick compared to clocks on the ground, and the difference comes out to about 38 millionths of a second every day. That sounds like nothing. But if the system ignored Einstein and did not correct for it, your position would drift by about 10 kilometers every single day. Your navigation would be useless within hours. Every time you follow a map on your phone, you are trusting that space-time really does bend, exactly as Einstein said. The curvature of space-time is not exotic. It is in your hand right now. The effect is so real that physicists have measured it on the scale of a single room. Take two of the most precise atomic clocks ever built. Put one on the floor and raise the other up by about 1 foot, and the higher clock ticks faster because it sits in slightly less curved space-time. By an unimaginably small amount, your head is aging faster than your feet. Time is not a universal river. It runs at different rates depending on exactly where you stand and how fast you move. And the greatest confirmation of all came in the year 2015. Far out in the universe, more than 1 billion years ago, two black holes spiraled into each other and collided, and the violence of that collision sent ripples racing outward through the fabric of space-time itself, waves in the cloth, stretching and squeezing space as they passed. After travelling for over 1 billion years, those ripples reached the Earth, and an instrument called LIGO felt them, a stretching of space smaller than the width of a single proton. We did not just infer the fabric of space-time anymore, we felt it ring like a bell. So here is where Einstein leaves us, and here is the crucial turn that sets up everything to come. Einstein took Newton's fixed, rigid stage and made it flexible. He made it bend, stretch, ripple, and curve. Space and time became dynamic, alive, responsive to the matter inside them. It was the greatest revolution in the history of physics. But notice what Einstein did not do. He made the stage flexible, but it was still the stage. Space-time, in his picture, was still the fundamental fabric of reality, the bottom layer, the thing everything else was made of and happened inside. Einstein bent the floor magnificently. He never once asked whether there was a floor at all, whether space-time itself might be made of something deeper. And that assumption, that space-time is the fundamental fabric, holds up beautifully. It survives every test we throw at it, for 100 years, in the world of the large and the smooth. Right up until the moment you try to combine it with the other great theory of the 20th century, the theory of the very small. Because when general relativity meets quantum mechanics, the beautiful fabric does not just stretch, it tears. Is less than break time equals 1s. Is greater than... There are two theories in physics that stand above all the others, two towering achievements that describe reality with a precision that borders on the miraculous. We have already met one of them. General relativity, Einstein's masterpiece, rules the world of the large. It describes planets and stars and galaxies, the curving of space-time, the orbits of moons, and the collisions of black holes, and it does so with such accuracy that we can predict the ripples from a collision 1 billion light-years away and catch them with an instrument on Earth. Its space-time is smooth, continuous, gracefully curved, like the surface of a calm sea. The other great theory rules the world of the small, and it is called quantum mechanics. It describes atoms and electrons and particles of light, the behavior of matter at the tiniest scales, and it too is staggeringly accurate, in some cases matching experiment to better than 1 part in 1 billion. But the world it describes could not be more different from Einstein's calm sea. The quantum world is restless, grainy, and probabilistic. Down there, nothing sits still. Particles do not have definite positions until you look. Energy comes in lumps. Everything jitters and fluctuates, never quite settling, governed not by certainty but by probability. Where relativity is smooth, quantum mechanics is jumpy. Where relativity is exact, quantum mechanics deals in odds. Each of these theories is, in its own domain, among the most thoroughly tested ideas in the history of human thought. Neither has ever failed an experiment. And that is precisely the problem. Because the universe is one universe, it does not run relativity in the big rooms and quantum mechanics in the small ones and keep them politely separated. There must be places where both apply at once, where something is both extremely massive and extremely tiny. And at those places, the two theories have to agree. The center of a black hole is such a place. The very first instant of the universe was another. And when you try to make the two theories shake hands in those places, something goes badly wrong. Here is what happens in plain terms. Quantum mechanics insists that everything fluctuates, that nothing can hold perfectly still. So if you take quantum mechanics seriously and apply it to space-time itself, the smooth fabric of Einstein should start to boil. At small enough scales, space-time should churn and foam and fluctuate, the curvature flickering wildly from one tiny region to the next. And when physicists try to actually calculate what happens, to run the mathematics of a quantum space-time, the equations do not give a sensible answer. They give infinity. They spit out nonsense, predicting that certain quantities should be infinitely large, which is physics shorthand, for we have no idea what is going on here. After nearly a century of effort by some of the most brilliant minds alive, we still do not have a confirmed working theory of quantum gravity. The two pillars of modern physics simply do not fit together. So the natural question is, where exactly does this breakdown happen? How small do you have to go before the smooth fabric tears into quantum foam? The answer is a number called the Planck length, and it is small in a way that the human mind genuinely cannot picture. So let me try to help. The Planck length is about 1/millionth of a billionth of a billionth of a billionth of a centimeter. Numbers like that are meaningless until you anchor them. So here is the anchor. Imagine you took a single atom, already so small that millions of them would fit across the width of a hair, and you blew that atom up until it was as large as the entire observable universe, billions of light years across. If you scaled the Planck length up by that same enormous factor, it would still be smaller than an average tree. That is how far below the atom this scale lies. It is the suspected floor of space, the smallest distance that may have any meaning at all. And there is a matching scale for time, called the Planck time, which is the time it takes light to cross that impossibly small distance. It comes out to about 5 times 10 to the minus 44 seconds, which is a decimal point, followed by 43 zeros and then a 4. Here is the way to feel how brief that is. There are more Planck times in a single tick of 1 second than there have been actual seconds in the entire history of the universe, across all 14 billion years since the beginning. 1 second contains more of these smallest moments than the universe has contained seconds in its whole existence. Below that scale, the very idea of duration, of one moment following another, may simply stop making sense. The physicist John Wheeler, the same man who gave us that line about matter and space-time, had a name for what reality might look like down at this scale. He called it quantum foam. Picture the surface of the ocean, seen from an airplane, smooth and flat and serene, the way space-time looks to us at human scale. Now drop down to the surface itself in a storm, and that smoothness explodes into chaos, into spray and froth and churning bubbles that appear and vanish in an instant. Wheeler's idea was that space-time might be exactly like that, smooth and gentle when you stand far back, but at the Planck scale, boiling, frothing, with tiny bubbles of space and time forming and popping out of existence, and perhaps even microscopic wormholes flickering in and out. At that level, there may be no stable distance to measure and no steady duration to count. The calm fabric we trust would be the distant view of something that, up close, never holds still for an instant. But the most unsettling crack of all is not about how small things get. It is something far more philosophical, and it cuts straight to the second half of our title. When physicists try to write down the most fundamental equation for a quantum universe, the master equation that would describe everything quantum mechanically, including gravity, they reach for something called the Wheeler-DeWitt equation. And when they write it down, something extraordinary happens. The variable for time disappears. It is simply not there. The deepest candidate equation we have for the universe as a whole contains no time at all. It describes a reality that just is, frozen, complete, timeless, with no ticking, no flow, no before and after written into it anywhere. Sit with how strange that is. We started this journey with time as one of the two most certain things in existence, the steady river carrying us forward. And now, at the most fundamental level we can reach, when we write the most basic law we can imagine for the entire cosmos, time falls out of the mathematics entirely. It is as if the universe, at bottom, does not know what time is. And if time is not in the fundamental equation, then maybe time is not fundamental. Maybe time is like temperature after all, something that has to emerge from a deeper reality that has no time of its own. This is the tear in the fabric. Down at the Planck scale, both of our great certainties dissolve. Distance loses its meaning. Duration loses its meaning. Space and time, the two things you have trusted your entire life, both seem to evaporate into something we cannot yet describe. And I want you to notice that this is not a frightening place, even though it sounds like one. It is a doorway. It is the exact spot where the old picture ends and the real question begins. Because if space and time are not the floor, then standing right here at the tier, we finally get to ask the question that drives everything that follows. What is space actually made of, down there beneath the smallest scale? Is it smooth, all the way down, an unbroken fabric? Or is it grainy, like a photograph that dissolves into pixels when you look too closely? Is less than break time equals 1s? Is greater than? The question of what space is made of sounds almost childish when you say it out loud, the kind of thing a curious kid asks before they learn not to. But it is one of the most serious questions in physics, and the honest answer is that nobody yet knows. There are, however, two leading ideas, and both of them say something radical. Both of them say that space is not the smooth, featureless emptiness it appears to be. Both say it has a structure, a texture, a microscopic anatomy, the same way a smooth photograph turns out to be made of pixels when you bring it close enough to your eye. The first idea is called loop quantum gravity, and its central claim is that space comes in chunks. According to this picture, you cannot keep dividing space into smaller and smaller pieces forever. Eventually, you hit a smallest possible unit, a tiny, indivisible grain of volume, below which the word smaller has no meaning at all. In this view, space is woven out of a network of these grains, connected together in a structure that physicists call a spin network, and what we experience as smooth, continuous space is really just an enormous number of these tiny chunks stitched together, far too small for us to ever notice the seams. There is a smallest possible area, a smallest possible volume, a fundamental graininess built into the fabric of space itself. The second idea is even more stripped down, and it is called causal set theory. It proposes that the most basic ingredient of reality is not chunks of space, but individual events, single happenings, connected to one another only by the relationships of cause and effect. This event could have influenced that one. That one came after this one. Out of nothing but a discrete collection of events and their causal order, the smooth space-time of our experience is supposed to emerge as an approximation, the way a beach looks like a continuous surface from a distance, even though it is really countless separate grains of sand. Now, you might wonder whether we could ever test such a thing, whether the graininess of space is forever beyond our reach. And the beautiful answer is that we might actually catch it. If space really is pixelated at the smallest scale, then light of different colors traveling across enormous distances might be affected ever so slightly differently by that graininess, arriving at fractionally different times after a long enough journey. So astronomers watch the light from gamma-ray bursts, titanic explosions billions of light-years away, looking for any sign that the different colors got smeared apart by the texture of space along the way. So far, the results show space looking perfectly smooth, right down to scales astonishingly close to the Planck length. That does not prove space is smooth, but it puts tight limits on just how grainy it is allowed to be. I want to be honest with you about the status of these ideas, because that honesty is part of what makes this channel worth your time. Loop quantum gravity and causal set theory are serious, mathematically careful research programs pursued by serious physicists, but neither one is confirmed. They are competing pictures, not established facts, and they sit alongside other approaches as candidates for the truth, not the truth itself. We do not yet know which, if any, is right. But here is what matters for the journey we are on, the thing I want you to carry forward out of this. Whether space turns out to be grainy chunks, or a web of causal events, or something else entirely, all of these pictures agree on the one radical point that should give you pause. Space has a microscopic structure. It is built out of something more basic than itself. It is not the smooth, empty, featureless given that Newton imagined, the eternal container waiting in the background. It is made of something, and once you accept that space is made of something, the only question left is what that something is, and where in the universe we might find the clearest clue to its identity. As it happens, the clearest clue comes from the most extreme and frightening objects that exist, the places where space-time is bent so violently that it folds in on itself completely. To find out what space is made of, we have to fall toward a black hole. Is less than break time equals 1s is greater than. A black hole is the closest thing the universe has to a place where space-time breaks. It is a region where so much mass has been crushed into so small a space that the fabric curves all the way around and seals itself off, creating a boundary, a surface called the event horizon, beyond which nothing, not even light, can ever return. For most of the 20th century, physicists treated black holes as the ultimate dead ends, regions of pure gravity, simple and featureless, defined by almost nothing but their mass and their spin. But in the 1970s, two physicists looking carefully at the mathematics of these objects uncovered something that would quietly detonate under the foundations of physics, and we are still living in the blast. The two physicists were Jacob Bekenstein and Stephen Hawking, and the puzzle they were chasing had to do with order and disorder. There is a sacred law in physics, the second law of thermodynamics, which says that the total disorder of the universe, a quantity called entropy, can only ever increase. Disorder always wins in the end. But black holes seem to threaten this law. If you took a hot, messy, high-disorder object and dropped it into a black hole, it vanished behind the horizon, and its disorder seemed to vanish from the universe along with it. The total entropy would go down, which the law forbids. Something was wrong. The resolution was as elegant as it was shocking. Bekenstein and Hawking showed that a black hole is not a featureless dead end at all. It has entropy of its own, an enormous amount of it, and therefore it has a temperature, and it even glows, ever so faintly, with a radiation we now call Hawking radiation. The disorder that falls in is not erased. It is added to the black hole's own immense store of hidden information. The law is saved. But saving the law required accepting a fact about black holes that turned out to be far stranger than the puzzle it solved. Here is that fact, and it is the single most important clue in our entire story, so I am going to say it slowly. The amount of information a black hole can hold, its entropy, is not proportional to its volume. It is proportional to its surface area, to the area of the horizon, the two-dimensional boundary, not the three-dimensional space inside. Stop and feel how wrong that should be. Think about how storage works everywhere else in your life. If you want to store more stuff, you need a bigger volume. A larger box holds more than a smaller box, and it holds more because it has more room inside, more cubic space. Double the size of a warehouse in every direction, and you get 8 times the storage, because storage goes with volume. That is the common sense rule of the entire physical world. But a black hole breaks that rule completely. Its capacity to store information grows with its surface, with the area of the boundary wrapping around it, as if all the information were somehow written on the surface, rather than filling up the inside. It is as though you discovered that a library could only ever hold as many books as you could paste pages onto its outer walls, and the enormous space within counted for nothing at all. And the numbers involved are beyond enormous. The information on a black hole's horizon is counted in tiny pixels, each one about a Planck area in size, that smallest possible patch of space we talked about earlier. Even a relatively modest black hole has a horizon covered in so many of these pixels that it could encode more information than every book, every hard drive, every word ever written or spoken by every human who has ever lived, and then multiply that by numbers so large they have no names. The boundary of a black hole is the most information-dense surface in the universe, and all of that information lives on the surface, not in the volume. There is a famous puzzle that grew directly out of all this, and it forced physicists to take the surface storage seriously rather than dismissing it as a quirk. It is called the black hole information paradox, and it goes like this. Quantum mechanics has an iron rule that information can never truly be destroyed. Whatever falls into the world, in principle, leaves a trace that could always be reconstructed. But a black hole seems to swallow things forever, and Hawking showed that it slowly evaporates, leaking away as that faint radiation, until, after an unimaginable stretch of time, it vanishes completely. So where did the information about everything that fell in go? If it simply disappeared when the black hole evaporated, that would shatter the deepest rule of quantum mechanics. The fight to resolve this paradox, which has raged for decades and is still not fully settled, kept dragging physicists back to the same strange clue that the information was somehow stored on the horizon, on the surface, all along, written on the boundary in a code we are only beginning to read. This discovery cracked something open in the minds of the physicists who took it seriously. Because if the true information content of a black hole is set by its boundary and not its interior, then maybe, just maybe, the interior is not where the real action is. Maybe the three-dimensional space inside the black hole, all that volume, is somehow secondary, a kind of projection or consequence of the information living on the two-dimensional surface around it. Maybe the inside is the emergent thing, and the boundary is closer to the source code of reality. And this is exactly the trail we have been hunting. Remember the question we carried out of the last part. Space is made of something, and we want to know what. Here, in the mathematics of black holes, we get our first hard, rigorous mathematical clue. We get the first serious suggestion that the volume of space we live inside might not be fundamental at all, that it might be a projection of information stored on a distant surface. The three-dimensional room around you might be the picture, and the real data might live on the boundary. For most physicists in the 1970s, this was a curiosity about black holes, a strange feature of these strange objects, and nothing more. But a few bolder minds asked a question that changes everything. They asked, what if this is not just a fact about black holes? What if the information in any region of space, including the perfectly ordinary region around you right now, is really written on its boundary? What if everything, the whole universe, works the way the black hole does? That question, taken seriously, leads to the most radical idea in all of modern physics. An idea that sounds insane the first time you hear it, and only gets stranger the more carefully you look. It is the idea that the entire universe, everything you have ever seen or touched might be a hologram, is less than break time equals 1s, is greater than. Let me connect this back to where we just were, because the leap we are about to make grows directly out of the black hole. We learned that a black hole stores its information on its boundary, on the two-dimensional surface of its horizon, not in the three-dimensional volume inside. Two physicists, Gerard Hooft and Leonard Susskind, looked at that fact in the early 1990s and asked the question that no one had dared to ask. What if this is not special to black holes? What if it is a universal law of space itself? And that question is not a detour from our central mystery. It is the strongest lead we have ever found for what space really is. The idea they proposed is called the holographic principle, and here is the cleanest way I can state it. The maximum amount of information that can fit inside any region of space is set not by the volume of that region, but by the area of the surface surrounding it. Every region of space, this whole room, the solar system, the entire observable universe, has a limit on how much information it can contain, and that limit is written on its boundary, which leads to a conclusion that should make the hair on your arms stand up. If everything inside a region can be fully accounted for by information on the surface around it, then, in a very real sense, the three-dimensional interior can be completely described by data living on a two-dimensional boundary. The inside is the projection. The surface is the source. The name comes from the holograms you have actually seen, the shimmering images on a credit card or a banknote. A hologram is a flat, two-dimensional piece of film, and yet when the light catches it correctly, a full three-dimensional image leaps out, with depth and perspective, an entire scene encoded on a flat surface. The holographic principle says that reality might pull off the very same trick, but on a cosmic scale. The three-dimensional world you move through, with all its volume and depth and distance, might be the projected image, and the true description, the real film, might live on a distant two-dimensional boundary. I know how this sounds, and I want to slow down for a moment so the strangeness lands properly rather than washing over you. The claim is not that the world is fake, or that you are trapped in some illusion. The claim is far more interesting than that. It is that there are two completely accurate ways to describe reality, and one of them uses fewer dimensions than the other. The three-dimensional description, with its space and its volume and its gravity, is true. And the two-dimensional description, living on the boundary, with no gravity and one fewer dimension, is also true, and it contains every single thing the bigger description contains, with nothing left out. When you have two equally complete descriptions and one is simpler, physicists have learned over and over through history to suspect that the simpler one is closer to the foundation. And the simpler one, here, is the one without the extra dimension of space. The space, the volume, the room to move, is the part that looks like it was added on top. For a few years, this was a bold conjecture, without a concrete example, a hunch that something like this should be true. And then, in 1997, a physicist named Juan Maldacena found the example, and it became the most famous and most cited idea in modern theoretical physics. What Maldacena discovered is technical, but the essence of it is something you can grasp, and it is staggering in what it implies. He found a specific kind of imaginary universe, one with gravity and an extra dimension of space, a universe where things fall and space-time curves, and he proved that this entire universe, gravity and all, is perfectly and completely described by a different theory, a quantum theory with no gravity at all, living on the lower dimensional boundary at the edge of that universe. Let me make sure you feel the force of that. He has two descriptions of the same thing. One description has more dimensions, has gravity, has curved space-time, with the works. The other description has fewer dimensions, no gravity, and lives only on the boundary. And they are exactly mathematically equivalent. Every event in the gravitational universe corresponds precisely to something happening in the boundary theory, and vice versa. The two are the same reality told in two languages, which means the gravity and the extra dimension of space and the curved fabric are not fundamental. They are emergent. They are the projected image cast by the boundary theory, which has no gravity and no extra dimension at all. In this universe, space and gravity literally arise out of something more basic that does not contain them. This is the bombshell, and it is why this single result has been built upon by thousands of physicists for almost 3 decades. For the first time, we had not just a hunch, but a precise, worked-out, mathematically airtight example in which space and gravity are emergent, in which a whole spacious universe is the projection of information living on its edge. The dream of the holographic principle became a theorem, at least in this one carefully constructed case. Now I have to be honest with you about that case, because honesty is the whole point of taking this seriously rather than turning it into a fairy tale. Maldaceno's universe is not quite our universe. The imaginary universe where the mathematics works perfectly has a particular shape, curved in on itself in a way that physicists call anti-de Sitter space, something like a saddle or a hall of mirrors that folds back on itself. Our universe is not shaped like that. Ours is expanding, flying apart, with a different geometry entirely. So what Maldacena gave us is a proof of principle, an existence proof, a demonstration that emergent space is genuinely possible and mathematically consistent. It is not yet a proof that our own universe works this way. That gap between the toy universe where it provably works and the real universe we live in is one of the great unsolved problems we will come back to. But even with that caveat, the achievement stands, and it changes the entire conversation. Because of Maldacena, the claim at the center of our whole journey that the space around you is not the foundation of reality, but a projection of something deeper, stopped being philosophy and became mathematics. It became something you could calculate. Holography is the strongest concrete evidence we have ever found that space is emergent, that the room you are sitting in is the picture and not the source, that the deeper reality is information living on a boundary, which leaves one more question burning, the most natural question in the world. If space is a projection of boundary information, then what exactly is that information, and how does it weave itself into the smooth, connected space we experience? The answer turns out to be the single most quantum thing in all of physics, the strange phenomenon that even Einstein could not stomach. Is less than break time equals 1s, is greater than, we have arrived at the most beautiful idea I know of in all of physics. So let me set it up carefully, because it answers the exact question we have been carrying. If space is a kind of projection of information living on a boundary, then there has to be something that stitches that projection together, something that decides why 2 points are close and another 2 are far, something that weaves the scattered information into a single, smooth and connected space. And the astonishing answer that has emerged over the last 15 years is that the thread doing the stitching is quantum entanglement. That answer is not a side note. It is the missing piece of our central question, the thing space might actually be made of. First, I need to make sure you understand entanglement itself, because it is the strangest fact in quantum mechanics, the one Einstein hated so much he called it spooky action at a distance. When two particles become entangled, they share a single, linked quantum state, so that they are no longer fully separate things. Measure one, and you instantly know something about the other, no matter how far apart they are, whether they sit side by side or on opposite ends of the galaxy. They behave like two ends of one object, connected in a way that has nothing to do with any signal passing between them. Entanglement is a kind of correlation woven into the very fabric of quantum reality, a togetherness that distance does not weaken. Now here is the thought experiment that cracked this whole thing open, and it belongs to a physicist named Mark van Ramsdonk, who around the year 2010 was playing with Maldaceno's holographic universe and asked a simple question: what happens to the space if I start removing the entanglement? He took two regions of space, described holographically by information on the boundary, and in the mathematics, he gradually turned down the entanglement between the parts of the boundary that corresponded to those two regions. And something extraordinary happened in the equations. As the entanglement decreased, the space between the two regions began to stretch. The distance grew. The two regions drifted apart, and when he removed the entanglement entirely, the space pinched off completely, splitting into two separate, disconnected universes with no space between them at all, because there was no longer any between for space to occupy. Let me say what that means, because it is staggering. It means distance itself might be entanglement made visible. 2 points in space are close to each other because the underlying quantum information describing them is highly entangled. 2 points are far apart because their underlying information is only weakly entangled, and if you could sever the entanglement completely, the 2 points would not just be far apart. They would no longer share a space at all. Space, in this picture, is not a pre-existing container that things sit inside. Space is a map of entanglement. It is what a web of quantum correlations looks like from the inside. The smoothness and connectedness of the world around you would be the smoothness and connectedness of the entanglement underneath it. This was not just a lone intuition, it connected to a precise mathematical result discovered a few years earlier in 2006 by two physicists named Shinsei Ryu and Tadashi Takayanagi. They found a formula that linked the two ideas we have been circling. The amount of entanglement between two regions, they showed, is measured by the area of a particular surface inside the curved space. Entanglement on one side, geometry, actual area on the other, joined by an exact equation. This is the bridge between everything we have discussed. The black hole told us information equals area. Holography told us the interior is a projection of the boundary. And now Ryu and Takayanagi tell us that the geometry of space itself, its very shape and size, can be computed directly from the pattern of entanglement in the underlying quantum information. Geometry is entanglement, written in the language of area. Out of all of this grew a research program with a name that captures the whole vision in 3 words. It is called IT from qubit. A qubit is a quantum bit, the most basic unit of quantum information, and the slogan means that the IT, the stuff of reality, space-time itself, is built out of qubits, out of quantum information knitted together by entanglement. In this picture, space-time is not the stage, and not even the fabric. It is a tapestry, woven thread by thread out of entangled quantum bits, and what we call geometry, distance, curvature, the shape of the world, is simply the large-scale pattern of that weave. The idea reaches its most vivid form in a conjecture from 2013 proposed by Maldacena together with Susskind, with a name that looks like a little equation. They wrote ER equals EPR. On one side, ER stands for the wormholes of general relativity, the bridges through space-time that Einstein studied. On the other side, EPR stands for quantum entanglement, named after a famous paper by Einstein and 2 colleagues. And the conjecture says these 2 things, the space-time bridge and the quantum entanglement, might be the very same phenomenon seen from 2 different angles. 2 entangled particles, in this view, are connected by a tiny, untraversable wormhole, a thread of space-time geometry that is identical to the thread of their entanglement. Entanglement and the bridges of space would not be 2 different things at all. They would be one thing, wearing 2 faces. Let me give you a way to hold all of this in your mind before we go on, a picture you can keep. Imagine the smooth, ordinary space of the room you are in right now as a tapestry, a single woven cloth, and imagine that the threads of that cloth are entanglement, countless quantum threads tying every part of the room to every nearby part. Now imagine pulling those threads out, one by one. The room does not slowly empty. It does something far stranger. It comes apart. It dissolves into disconnected scraps that no longer share any space, because the space was never the cloth. The space was the weaving. The space was the entanglement, holding it all together. There is a consequence of this that I find quietly astonishing, and it is worth drawing out before we go on. If distance is entanglement, then the reason you cannot instantly be on the other side of the galaxy is not that some enormous empty gulf physically separates you from it. It is that you and that far-off place are barely entangled, your underlying quantum information only faintly correlated, and that faintness is what we experience as enormous distance. Nearness and farness, in this picture, are not about a pre-built space that things are scattered across. They are about how strongly the underlying information is woven together. Two things are near because their quantum threads are tightly knotted, and far because those threads are loose. The whole sprawling geometry of the cosmos, the billions of light years between galaxies, would be a map of how entanglement is distributed, nothing more and nothing less. And this reframes gravity itself in a way that would have stunned Newton and even surprised Einstein. If geometry is built from entanglement, then the curving of spacetime that we call gravity is really a story about how that entanglement is arranged and rearranged. Mass and energy change the pattern of entanglement in the quantum information underneath, and that changed pattern shows up on the screen of our experience as curved space, as the bending of paths, as the force that holds you in your chair and keeps the planets in their orbits. Gravity, the oldest force we know, the one you feel every waking second, might be nothing but entanglement seen from the outside, the large-scale shape of the quantum weave. I have to flag honestly where this stands, because we are now standing at the living frontier of physics, not on settled ground. This entanglement picture of space is the leading research direction pursued by many of the best physicists alive, and it is suggestive in the most profound way, supported by precise results like the Ryu-Takayanagi formula, but it is still mostly proven inside those idealized holographic universes, the saddle-shaped ones, not yet fully established for our own expanding cosmos. It is the best lead we have, not a closed case, but take it seriously for a moment because of what it does to our central question. If this picture is right, then space is not fundamental. Space is what highly organized quantum entanglement looks like from the inside. The true floor of reality is not a stage and not a fabric, but a web of pure quantum information, and everything we call distance and shape and geometry is the pattern that web happens to form. We have answered, at least provisionally, the first half of our title. We have a real candidate for what space might really be. But that leaves a question that nags immediately, and it is the question that separates a beautiful idea from a piece of science. Is any of this testable? Or are we just telling ourselves an elegant story on a chalkboard that the universe will never let us check, is less than break time, equals 1s is greater than? I want to bring you right up to the present moment now, to the last couple of years, because something has shifted. And it is the reason this topic feels so alive right now, rather than like a piece of settled history. For a long time, the idea that space-time emerges from quantum information lived almost entirely on chalkboards, in the most abstract reaches of theoretical physics. But in the years around 2025 and 2026, the ground has been moving on two fronts at once, and both of them matter for our central question. On the theoretical front, physicists have been pushing the idea further than ever, and the direction of travel is telling. Recent work has reframed gravity itself, the force Einstein explained as the curving of spacetime, as something that emerges directly out of quantum information. In these new approaches, the geometry of spacetime is treated as a quantum quantity, something that can be in a state of uncertainty like any other quantum thing, and gravity's familiar pull is recast as a kind of bookkeeping of information, the universe keeping track of how its quantum pieces are arranged. There is a line of work with a name that sums up the whole program on emergent holographic spacetime arising from quantum information, continuing to show that gravitational spacetime can be reconstructed piece by piece from a pattern of entangled qubits. What makes this feel like real momentum rather than wishful thinking is where it is coming from. The same picture is being approached from completely different directions by people who started from different places. String theorists arrive at it from their study of holography. Quantum information theorists arrive at it from their study of entanglement and qubits. People working on the mathematics of black holes arrive at it from yet another angle, and they keep converging on the same conclusion, that spacetime is emergent from quantum information. When independent groups, using different tools and different starting assumptions, keep arriving at the same destination, that is one of the strongest signs in science that an idea is onto something real. But I promised you honesty, and the honest picture includes a serious gap, the same one I flagged earlier, because it is the central unsolved problem of this whole field. The strongest, cleanest results still live in those idealized universes, the saddle-shaped anti-de Sitter spaces where the mathematics behaves. Nobody has yet built the complete, rigorous version of this story for our actual universe, the real one that is expanding and flying apart around us. Bridging that gap, getting from the toy universe where emergence provably works to the real cosmos we inhabit, is the great unfinished task. We are in the middle of the revolution, not standing triumphantly at the end of it. Anyone who tells you it is all figured out is selling you something. And now the second front, the one that genuinely thrills me, because it is the answer to the question we ended the last part on. Is this testable? For most of its life, the idea that spacetime is quantum seemed hopelessly beyond experiment, locked away at the Planck scale where no instrument could ever reach. But that is starting to change. In 2026, physicists published a framework that sorts the possible fluctuations of spacetime into different types and works out the distinct signatures each type would leave behind, signatures that instruments might actually detect, from the enormous gravitational wave detectors like LIGO down to compact, sensitive systems sitting on a laboratory bench. The question of whether spacetime itself trembles and fluctuates is being turned slowly and carefully into something we can measure. The experiment that captures the dream most directly has a clunky name but a stunning ambition. It is called the quantum gravity-induced entanglement of masses, and the idea behind it is almost cheeky in its simplicity. Take two tiny objects, small but still massive enough to feel each other's gravity, and place each one into a quantum superposition, a state where it is, in a sense, in two places at once. Then let them sit near each other, interacting through nothing but their mutual gravity, and watch carefully to see whether they become entangled. Here is why that would be momentous. According to our best reasoning, gravity can only create entanglement between two objects if gravity is itself quantum. If those two little masses come out entangled, with nothing but gravity passing between them, it would be the first direct evidence that the gravitational field, and therefore the curvature of spacetime itself, obeys the rules of quantum mechanics. Recent versions of the proposal have even added a third mass to make the delicate signal more robust against the disturbances that constantly threaten to wash it out. I do not want to oversell how hard this is, because the difficulty is part of what makes it beautiful. These experiments require keeping fragile quantum states alive in objects almost large enough to see for whole seconds at a time, while shielding them from every stray vibration and particle that could ruin the superposition. It sits at the absolute edge of what is technologically possible. But edge is the key word. It is no longer science fiction. It is engineering, hard engineering, but engineering, the kind of problem that gets solved given enough time and ingenuity. It is worth pausing on why detecting that entanglement would settle so much, because the logic is cleaner than you might expect. Think about what gravity is in this experiment. It is the only thing passing between the two little masses. If gravity is just a classical field, a smooth Einsteinian curvature with no quantum nature, then it cannot create entanglement, because entanglement is a quantum resource, and a purely classical messenger cannot deliver it. It would be like trying to send a secret-coded message through a courier who can only shout the same word over and over. But if the two masses do come out entangled, then whatever passed between them, gravity, must have carried quantum information, must itself have been in a quantum superposition, must have been quantum to its core. And since gravity, in Einstein's picture, simply is the curvature of space-time, proving gravity is quantum would be proving that space-time itself is quantum, that the fabric we have been questioning all along really is woven from quantum threads. One tabletop measurement, and a century-old question cracks open. And every single one of these efforts, the theoretical convergence and the experimental ambition alike, is aimed at exactly the same target we have been walking toward this entire time. They are all trying to find out whether space-time is the floor of reality or the wallpaper on top of something deeper. They are trying to do it not with philosophy and not with elegant arguments on a chalkboard, but with real instruments measuring real quantities. The generation of people alive right now, the people watching this, may turn out to be the first humans in history to get a genuine, experimental answer to a question our ancestors could only wonder about under the stars. But notice something. Now that we are nearly there, we have spent almost all of our time on one half of the title. We have watched space dissolve into entanglement, watched it become a projection, a tapestry of quantum information. We have barely touched the other half, the stranger and more personal half, the half that you feel in your chest every time you watch an evening slip away. We have not really dealt with time, and time, it turns out, refuses to behave. Time is even harder to pin down than space, and when you chase it down to the bottom, it may not be there at all. Is less than break time equals 1s is greater than break. We have watched space melt. We watched it go from Newton's fixed container to Einstein's bending fabric, to a tapestry woven from quantum entanglement. So now, the central question of our whole journey turns to face space's twin, the second word in our title, and asks the obvious thing. Is time any more fundamental than space turned out to be? Or does time too dissolve when you look closely enough? And to answer that, we have to start with the single most baffling fact about time, a puzzle so profound that physicists have argued about it for over a century. Here is the puzzle. Almost every fundamental law of physics works exactly the same, whether you run it forwards or backwards. Watch two billiard balls collide in slow motion, then watch the film in reverse, and both versions obey the laws of physics perfectly. There is nothing in the equations that says which way is forward. At the level of individual particles, the laws are blind to the direction of time, completely symmetric, with no preference for past or future. And yet your entire experience screams the opposite. You remember the past, never the future. You grow older, never younger. Things break, but do not unbreak. You feel time flowing in one direction, relentlessly, like a river that only ever runs one way. So where does that one-way flow come from if the underlying laws do not contain it? The answer, as far as we can tell, comes from a single law, the one law in physics that does have a direction built into it, the second law of thermodynamics. It says that entropy, the amount of disorder in a system, tends always to increase. And the one-way arrow you feel, the difference between past and future, seems to come entirely from this statistical drift from order toward disorder. Time's direction is not woven into the deepest laws. It emerges from the overwhelming tendency of things to get more jumbled. Let me make that concrete with the homeliest examples I can find, because this is one of those ideas that sounds abstract until you ground it in a kitchen. A coffee cup falls off the table and shatters into 100 pieces. You have never once seen 100 pieces leap off the floor and assemble themselves back into a cup. Stir milk into your coffee and it swirls and spreads until the whole thing is an even brown. You have never seen the brown spontaneously unmix back into white milk and dark coffee. Why not? Not because the reverse is forbidden by any law. Every individual molecule in that reverse process would obey physics perfectly. It is because the orderly arrangement, the intact cup, the separated milk, is just one possibility among a near infinite number of disorderly ones. Disorder is overwhelmingly more likely, so things drift toward it, and that drift, that statistical avalanche from the rare ordered states toward the countless messy ones, is the arrow of time. It is not a fundamental flow. It is a kind of accident, an accident that began with a universe in an extraordinarily ordered, low disorder state at the moment of the Big Bang, and has been unwinding ever since. And now recall something we learned all the way back with Einstein, because it deepens the mystery in a way that is going to matter. We saw that simultaneity is relative, that there is no universal now sweeping through the cosmos. Two observers moving differently genuinely disagree about whether two distant events happened at the same time. So already, before we even get to quantum mechanics, relativity has told us that the present moment is not a universal thing. Your now and the now of a distant galaxy need not agree at all. There is no master clock, no cosmic instant that is happening everywhere at once. Take that seriously, and you arrive at one of the strangest pictures in all of physics, a picture called the block universe. If there is no universal present, if every observer slices time differently, then the mathematics of relativity suggests that past, present, and future may all exist equally, all at once, as a single, frozen, four-dimensional block. In this picture, the moment of your birth and the moment of your death and this very moment of you listening are all equally real, all sitting there in the block of space-time like frames already printed on a reel of film. And the flowing now that you feel so vividly, the sense that this instant is special and is sliding forward into the next, may not be a feature of the universe at all. It may be a feature of you, of your mind, of the way a conscious creature with memory experiences a block that is, in itself, completely still. Sit gently with the vertigo of that, because I do not want it to frighten you, only to open you. The moment you are living right now, this exact instant, might be no more genuinely the present than any other slice of the block. Every moment thinks it is now. The you of 10 years ago, frozen in the block, is just as convinced that their moment is the real present as you are convinced of yours. From inside, every frame of the film feels like the now. The flow may be the story your mind tells as it moves through a still field of moments that are all, in truth, already there. I should flag clearly that this is genuinely contested because intelligent people disagree about it and the science cannot fully settle it. Whether only the present moment is real, a view called presentism, or whether all moments exist equally, a view called eternalism, is fiercely argued at the border between physics and philosophy. The mathematics of relativity leans hard toward the block, toward eternalism, but it cannot completely close the case, and honest physicists admit it. What I can tell you is which way the evidence tilts, and it tilts away from the flowing now you feel and toward the frozen block, you cannot. It helps to understand why the universe started in such an ordered state, because that single fact is doing an enormous amount of work. Every coffee cup that shatters, every memory you form, every moment you experience as flowing forward, all of it traces back to the fact that the universe began 14 billion years ago, in a condition of extraordinarily low disorder, almost impossibly smooth and ordered. From that special beginning, disorder has been climbing ever since, and that long climb is the river you feel yourself carried along. If the universe had begun in a state of high disorder, already jumbled, there would be no arrow at all, no past distinct from future, no flow. So the direction of time, the most basic and inescapable feature of your existence, may rest entirely on the peculiar tidiness of the universe's first instant, a kind of cosmic accident frozen into the beginning of everything. Pull that one thread, the orderly start, and the entire experience of time flowing forward unravels with it. And here is why all of this matters for our one central question, the thread we have been following from the very first sentence. Just as space turned out to have no fundamental here, no privileged single point that is truly the center, time is turning out to have no fundamental now and perhaps no fundamental flow. The one-way arrow looks like statistics, not bedrock. The present moment looks like perspective, not physics. Time, the steady river you have trusted your whole life, is starting to look less like the master clock of the universe and far more like another emergent appearance, exactly, precisely as our central claim predicted, which raises the boldest question of all, the one that finishes the thought. If time has no real now and no real flow, could it be that time, like space, does not exist at the bottom of reality at all, that it has to emerge from something timeless underneath? Is less than break time equals 1s is greater than? If time has no preferred present moment, and if its one-way arrow is really just the statistics of disorder piling up, then we are pushed toward a question that sounds almost impossible to ask with a straight face. Could time itself, like space before it, emerge from a deeper layer of reality that contains no time at all? Could the bottom of the universe be not just spaceless but timeless, frozen, changeless, with time appearing only as a kind of illusion experienced from the inside? It sounds like mysticism. But it is a serious idea in physics, and there is a precise mechanism that shows how it could work. The mechanism was proposed back in 1983 by two physicists named Don Page and William Wooters, and once you see it, you cannot unsee it. Imagine the entire universe as a single quantum state that does not change at all, frozen and timeless, exactly the kind of state that strange Wheeler-DeWitt equation with no time in it seemed to describe. Now mentally divide that frozen universe into two parts. Call one part the clock, just some system that has different possible configurations, and call the other part the rest of the universe. The crucial move is that these two parts are entangled with each other, their states linked in that quantum way we discussed. Now here is the magic. From the outside, looking at the whole thing at once, nothing ever changes. The total state is frozen, timeless, eternal. But from the inside, if you are part of the rest of the universe, and you ask, what state am I in when the clock reads a particular value, you find that the rest of the universe appears to change as the clock advances. Time, real flowing time, emerges for the internal observer, even though the universe as a whole is utterly static. Let me say that again because it is so strange and so beautiful. The universe can be completely frozen as a whole, and yet an observer inside it, entangled with a clock, will experience the full flow of time, change, motion, before and after, a present sliding into a future. Time would not be a fundamental feature of the universe. It would be a relationship, a correlation between a clock and everything else, and it would emerge from entanglement, the very same phenomenon that we found weaving space together. And this is not merely a story told with equations. Physicists have built tiny laboratory versions of this idea around the year 2013 using entangled photons. They constructed a small toy universe in which one photon plays the role of the clock and another plays the role of the rest of the world entangled together. And they showed that an observer who measures the system from inside, relative to the clock photon, sees the other photon evolving and changing in time, while an observer who measures the whole entangled system from outside, all at once sees a static, unchanging, frozen state. The same little universe is timeless from one viewpoint and full of flowing time from another. Emergent time, demonstrated, at least in miniature, on a laboratory bench. I want you to notice the thread tying both halves of our title together now, because it is the most elegant thing in this entire story. The same culprit keeps appearing. Entanglement builds space, in the holographic picture, stitching distant points into a connected geometry. And entanglement builds the experience of time in the Page-Wouters picture, linking a clock to the world so that change can appear. The very same quantum phenomenon, this spooky togetherness that so disturbed Einstein, may be the single thread out of which both space and time, both halves of space-time, are woven. One thread, sewing the whole stage. The frontier has kept moving, right into the present. In 2025, physicists studying how the arrow of time emerges from sequences of quantum measurements found something that genuinely surprised them. They showed that an arrow of time can emerge when you make a series of measurements on a quantum system, which fits everything we have said. But they found something more. They found that under certain conditions, two arrows of time can emerge from the same quantum system, two directions of temporal flow, rather than the single relentless forward direction we take for granted. The details are subtle, but the headline is profound. Even time's most basic feature, its single forward direction, may not be fundamental. It may be just one way that quantum systems can organize their changes, not a law carved into the bones of reality. I have to be fair and tell you that this is a live and unsettled debate with brilliant people firmly on opposite sides, because that disagreement is part of the honest truth of where we stand. On one side stands a camp led by the physicist Carlo Rovelli, who argues that time is thoroughly emergent, that at the most fundamental level there is no time at all, that the flow we feel is an illusion produced by our limited, blurry view of a timeless reality. On the other side stands a camp led by the physicist Lee Smolin, who argues almost the exact opposite, that the passage of time is the one thing that is truly, fundamentally real, more real than space, and that it is space, not time, that emerges. Smolin even suggests that the laws of physics themselves might evolve and change in real, flowing time. These are not cranks arguing at the margins. These are serious, accomplished physicists who have looked at the same evidence and reached opposite conclusions, and the question remains genuinely open. There is a way to feel why the timeless picture is not as crazy as it first sounds, and it comes back to that frozen equation we met earlier, the Wheeler-DeWitt equation with no time in it. When that equation first dropped its time variable, most physicists treated it as a disaster, a sign that something had gone wrong. But the Page-Wouters idea flips the disaster into an explanation. Of course, the equation for the whole universe has no time in it, this view says, because time was never a feature of the whole universe. Time is what one piece of the universe experiences in relation to another piece. Ask the universe as a whole what time it is, and there is no answer, because the question only makes sense from inside, relative to a clock. It is a little like asking what is north of the North Pole. The question sounds reasonable until you realize that north is a direction defined on the surface, and at the very top there is simply no further north to point to. Time, in this picture, is a direction that exists for observers within the universe, not a property the universe possesses from outside. So I'm not going to pretend we have the final answer about time, because we do not. But notice what we do have, and how it bears on everything. What time really is turns out to be every bit as wide open, as unsettled, as profound a mystery as what space really is. And the same ideas, the same quantum information, the same entanglement keep showing up at the bottom of both questions. Which means we can finally pull the two halves of our title together into one statement, the statement this whole journey has been building toward. If space emerges from entanglement, and if time emerges from entanglement, then space-time itself, the entire stage, the whole fabric, the floor you thought you were standing on, is the emergent thing. And the true foundation of reality, underneath all of it, would be a timeless, spaceless web of pure quantum information. That is the answer the whole video has been walking toward. Now let me try, in the time we have left, to put it all together and to tell you what it might mean for you. Is less than break time equals 1s is greater than. Let me gather every thread we have followed and lay them side by side, because a picture has been forming, slowly, the way a photograph develops, and I think you can see it now in a way you could not at the start. We began with space and time as the most fundamental things imaginable, the fixed stage and the steady clock. And piece by piece, that picture has inverted itself. Newton's absolute container gave way to Einstein's bending fabric. Einstein's fabric tore when it met the quantum world. The torn edges revealed that space has a microscopic structure, that it is made of something. Black holes showed us that the something lives on boundaries, that information scales with surface, not volume. Holography turned that hint into mathematics, showing that a whole spacious universe can be the projection of information on its edge. Entanglement revealed the thread doing the weaving, suggesting that distance itself is entanglement made visible. And time, when we finally turned to it, dissolved in the very same way, its flow revealed as statistics, its present revealed as perspective, its existence, at the bottom, thrown into doubt by the same timeless quantum information underneath. Here is the metaphor that I think captures the whole thing, the one I want to leave you holding. Space-time may be the screen, and quantum information the code running underneath it. Think about how you use a computer or a phone. You see icons, windows, smooth images, a friendly surface you can touch and move through. You almost never see the actual computation underneath, the raw information being shuffled and processed, because you do not need to. The interface is built precisely so you can interact with the machine without ever confronting the code. And the suggestion at the center of modern physics is that space and time might be exactly that, an interface, a user-friendly display generated by a deeper layer of quantum information, and that we spend our entire lives reading the screen and mistaking it for the machine. Remember the analogy I gave you at the very beginning, the one about temperature, because we have now earned the right to take it seriously. Temperature is real. You feel it, you measure it, it governs your comfort and your survival. But it is not fundamental. It emerges from the motion of molecules that have no temperature of their own. A single atom is neither hot nor cold. Temperature is what trillions of them, moving together, look like from far away. And space and time, this whole story suggests, may be the same kind of thing. Real, measurable, governing everything you do, but emergent, arising from quantum ingredients that have no space and no time of their own. The pieces underneath would not be small bits of space. They would be something to which the words small and bit, near and far, before and after simply do not apply. I want to be completely honest with you about where this stands, because the honesty is what makes it worth believing rather than just enjoying. This is the leading direction in fundamental physics, supported by real and rigorous results, by holography, by the Ryu-Takayanagi formula, by the IT from qubit program, by the newest theoretical and experimental work of the last 2 years. But it is not proven for our universe. The cleanest results still live in idealized, saddle-shaped toy universes, not in the expanding cosmos we actually inhabit. We are somewhere in the middle of a revolution, not standing at its finish line, and the most important chapters may not be written yet. What would settle it is a complete emergent description of our own real universe, together with experimental confirmation from those tabletop quantum gravity tests and fluctuation searches we talked about, results that may well arrive within the lifetimes of people listening to this right now. And let me bring it home to you, personally, because this is not an abstract story happening somewhere else. The space you are sitting in at this very moment, the few feet of room around your body, and the time you are spending, this quiet stretch of evening sliding by as you listen, both of them may be emergent appearances of a deeper quantum order. And I want to be clear about what that does and does not mean, because people sometimes hear this and feel diminished. It does not make your space and your time any less real. Temperature is not fake because it emerges from molecules. A sunset is not fake because it is light scattering through air. Emergent does not mean illusory. It means your space and your time are real, just not fundamental. Real the way a melody is real, even though it is only air moving in patterns. It is worth sitting with why this idea keeps gaining ground rather than fading away, because that staying power tells you something. Throughout the history of physics, every time we found that something we thought was fundamental was actually made of smaller pieces, the universe got simpler and more unified, not more complicated. Heat turned out to be motion, and suddenly thermodynamics and mechanics were one subject. Light turned out to be electromagnetism, and two fields became one. Matter turned out to be atoms, and atoms turned out to be a handful of particles arranged in patterns. Each time, the surface complexity dissolved into a simpler layer underneath. The idea that space and time emerge from quantum information is the next step in that very old story, the boldest one yet, because it reaches all the way down to the stage itself. If it holds, then the deepest layer of reality is not a place and not a moment. It is a pattern of relationships, a web of information out of which place and moment are spun. And there is something almost vertiginous in realizing that the search for the foundation of everything keeps leading us not toward bigger and grander things, but toward something more abstract and more quiet than we ever expected. There is one last thread to tie off, and it reaches all the way back to the beginning, to a quiet objection raised 300 years ago. Remember Leibniz, who refused to believe space was a container and insisted instead that it was nothing but the relationships between things. After this entire journey, look how close the newest physics has circled back to that old idea. Perhaps space was never a container after all, and time was never a clock. Perhaps both are simply relationships, patterns of entanglement, the universe's way of organizing information so that it can be experienced from the inside. Leibniz, with no telescope and no equations of relativity, may have felt his way towards something that takes us our most advanced physics to even begin to confirm. And so this picture, strange as it is, does not leave you cold or small. It does something closer to the opposite. It makes reality more intimate, not less. Because if space and time are emergent, woven from a single web of quantum information, then at the most fundamental level, the level beneath all the distance and all the duration, you and the farthest galaxy you will never reach are made of the very same thing, threads in the same underlying fabric, with the apparent gulf between you being just a feature of the interface, not the floor. The separateness is on the screen. The connection is in the code. So what are space and time, really? After everything, here is the answer I can offer you, and it is the quietest and the most profound thing I know. The most ordinary experiences you have, the distance from your hand to the wall, the duration of a single breath, the steady passage of this evening into night, may turn out to be among the most profound mysteries in the entire universe. The stage you have stood on, unquestioning, your whole life. The space and time you have trusted more completely than anything else may be the deepest secret reality has been keeping. You have been standing inside the answer the entire time, living in it, made of it, breathing it, waiting only for someone to think to ask the question. And now you have asked it. So tonight, as the evening settles around you and the quiet grows, you can rest in the strangest and most comforting thought of all, that the universe is far more mysterious and far more woven together than the fixed and lonely stage you once believed in, and that you were never separate from it, not for a single moment, not even now.